we only left with about 10 slides. Okay, inshallah. So maybe we can finish at 11:30 macam tu. Okay. Okay, so for those who just enter during my lecture just now, actually we started at 9 a.m. Okay. I don't know whether you missed the message or you woke up late. We start so our class every week, every Thursday will be only on Thursday. Okay, not Wednesday we don't have class. So I change it to Thursday 9 a.m. to 12 p.m. Okay, unless if there is any one of you who have other class at 9 a.m., then we have to go back to the original. Okay, you have to inform me. Okay, otherwise I assume that you guys don't have any class at 9 a.m. So that's why I do straight 9 to 12. Okay, so every Thursday. Okay, so we continue about the open system. Open system control volume or properly selected region in space. Okay, I think this one already mentioned, open system. So for example here, what do we have here? Like a tank, a gas tank. Okay, so the tank is of the system, but it is an open, so we have to consider the change of mass fluid in and out of the control volume, one inlet and one exit. Means that if there is any fluid transfer, any mass, any particles, it will be we have to take into consideration that part when we analyze the system problem. Okay, one inlet and one exit. Okay, and then mass flow. Okay. Okay, it usually enclose a device that involves mass flow such as a compressor, turbine, or nozzle. Okay, so these are the main components in a thermodynamic cycle: compressor, turbine, nozzle. Even in aircraft cycle, aircraft engine cycle, gas power cycle, the main components in an aircraft cycle is compressor, turbine, plus nozzle. Nozzle is to enhance the speed, okay, the fluid to a high speed gas flow. Okay, so we need a nozzle. So this device, compressor, turbine, etc., it is considered as a open system, open system, open control volume. Okay, so both mass and energy can cross the boundary of a control volume. Okay, so for an open system, both mass and energy can be exchanged. Okay, can cross. But for closed system just now, only energy. No mass. Mass cannot be transformed or exchanged within the closed system. But for open, both mass and energy can cross the boundary of the control volume. Okay, so and then we call also control surface the boundaries of a control volume. It can be real or imaginary. Control surface is same as boundary. Okay, just another definition. Control volume can involve fixed, moving, real, imaginary boundaries. Okay, so these are example: a control volume with real and imaginary boundaries. So example, nozzle. So normally we design, okay, a sketch a nozzle like this, okay, from highest bigger area, okay, initial bigger area to a smaller area at the exit. Okay, nozzle involves change of area, okay, because if you remember the Bernoulli principle, if we change area, then the volume will change. The speed, the velocity will change. So so that's why a nozzle has to have change a different area, exit and inlet. Okay, so this is nozzle. CV is control volume. And another one B, for example, if you have a piston, okay, for example, combustion, a diesel engine, we what do we call it? Internal combustion engine. Okay, CI engine, right? Internal combustion, ICE, internal combustion engine for a car, a vehicle. Sometimes it use a piston engine. Okay, so that's why this one, a control volume B with fixed and moving memory as well as serial and imaginary binary. So in order for us to analyze, to characterize the engine process in a car engine, for example, vehicle. So we need to classify the boundary of the engine, okay, the piston engine or diesel engine, okay. And then properties of a system. So this is also some of the units, about units. So property and characteristic of a system. So some familiar properties, P, pressure, temperature, volume, mass. Okay, so these properties or physical values, okay, physical value that we are going to measure, okay, can be divided into intensive and extensive. Okay. uh, this definition that at least you know, but you don't have to remember. Okay, so intensive properties, those that are independent of the mass of the system, such as temperature, pressure, and density. While extensive, those values depends on the size of the system. Okay. Okay. So intensive, temperature, pressure, and density means that if the temperature uh, in a closed system, for example, like a rectangular here, the closed system here, the temperature, pressure, and density will not change if the mass means that, for example, if some of the mass is being transferred out, some of the particles is being transferred, the temperature, pressure, and density of this maintain is independent of the change of the mass, while the volume and apa tadi, and energy, okay, depends on the mass, okay, extensive properties. So there is another notation, okay. So when we write these extensive properties, we have to define whether it is in terms of mass or it is the original, the default value. For example, V volume here, if you write V small v, means that it is in terms of mass, volume, meter cube per kilogram. So the unit will be meter cube per kilogram. Okay. Otherwise, if you write this V, is just meter cube or centimeter cube or milliliter, okay. So this other values, enthalpy, you are going to use enthalpy for first law thermodynamics. So enthalpy is in joule per kilogram, joule per kilogram, okay, this one. But if you use H, big H, enthalpy is joule. Okay, so this extensive properties, normally it is in terms of mass per kilogram per gram. Okay, so in our calculation, we use a lot this mass. Okay, this massive this extensive properties. Okay, means that normally the values are given in terms of extensive property, which is in terms of mass. If you have what's it sebut, CP, specific heat, this specific heat is normally being given in terms of mass, so we have to write it in small letter. It is the unit is joule or kilojoule, or joule per kilogram per Kelvin. Okay, kilogram, sorry. But if it's in this capital letter, it's joule per Kelvin. But normally we use this one. Okay, means that we calculate, we measure, we analyze the system normally in terms of per mass, per kilogram mass. Memang the normal calculation. Okay. Yang ni tak apa, continuum, atom, okay, pass. Sorry, saya pass. Maybe not really important for our topic. Okay. Density and specific gravity. Okay, so density. Okay, density is mass per volume, kilogram per meter cube. Okay, and we call it specific volume. Okay, volume just now is if the volume is in terms of mass per kilogram. We write it as the small letter V, and we call it specific volume. The name is specific volume. Specific weight, specific gravity, specific enthalpy, specific entropy. Okay, specific normally is in terms of kilogram. Okay, so this specific volume is actually the opposite. Okay, the opposite of density, because it is written in okay, because V volume is kilogram. Okay, and the mass is V volume is meter cube, and habis kelas ni saya dah pening-pening dah. Okay, ni meter cube. Okay, so over kilogram, kan? Kilogram, meter cube, kilogram. So this is the unit of specific volume. So if you see this is actually the inverse of density. So if you have the volume, for example, in your the problem, the exercise give you the value of the specific volume, is actually you can means that you can calculate directly the density, only inverse. Okay, opposite. Specific weight, the weight of a unit volume of a substance. Okay, it's written in gamma, but this is seldom used. We use it very not quite often. Specific gravity also jarang-jarang guna lah. Okay, not quite often. Okay, only specific volume. Okay, state and equilibrium. Okay, equilibrium. There are a lot of definition for you today, but it's okay. It's just a definition. Like the most important part is that you know how to solve a problem. Definition is just for your information. Okay, state and equilibrium. Thermodynamics deal with equilibrium states. Of course, equilibrium is a state of balance. Okay, so normally before we analyze a problem, like I mentioned just now, if you have exercise or in your exam problems to solve, you write, okay, we consider first the system is what? Okay, the system include what? Include the piston, the cup of coffee and the surrounding, etc. Okay, so that is the system. Okay, and then you have to state also that the problem that you are analyzing, that you are studying, is the state of problems, the process where the problems is in equilibrium, is in balance. Okay, because otherwise, if we did not state, if we do not consider that the process is in equilibrium or is in balance, you cannot apply the some of the equation principal law. For example, energy balance equation, you will see this. Okay, energy balance equation. The energy balance equation is valid when you consider the system is in balance. So that's why you have to state that first. Okay. Normally in your research, or your project research, one day when you do a research, if you read articles, paper, right, from other scientists, researcher, normally they will state first the condition of the system that they are studying. They will state first we consider that the system is in this balance, energy balance state, it is in equilibrium, and then they analyze the problem. Okay, if you don't state that, then other people maybe we maybe can trigger you and will ask you whether there is a change of this, change of that in terms of the process. But if you already state that the system is balanced, so we understand that there is no change in, for example, the energy is balance. Okay, there is no other system interfere. Okay, so you have to state that a state of balance. In equilibrium state, there are no unbalanced potential that will fall within the system. Okay, there are no unbalanced potential. Okay, no unbalanced, so means that it is balanced. Okay, thermal equilibrium. So there is thermal equilibrium, mechanical equilibrium, phase equilibrium, chemical equilibrium. Okay, but normally if we state that the system is equilibrium, so we understand that all of these thermal, mechanical, phase, chemicals are all in balance. Okay, so you don't have to state one by one. Okay, so thermal equilibrium, if the temperature is the same throughout the entire system. Okay, so when we said that we are studying the system where it is in equilibrium, so we assume at a certain point, for example like this. Okay, you have to study again. Yeah. Tak boleh. Yeah. Okay, contoh. Okay, means that you have to state the period of time. Okay, the period of time that you are going to focus. Okay, maybe the whole process of the phenomenon. Okay, is throughout. Okay, bagi example lah. Okay, okay, the cup of coffee. Okay, sorry, I give example. Okay, for example, okay, you put the cup of coffee in a table in the living room for 5 hours, for example, 5 hours. Okay, but you want to study, you want to calculate the amount of heat transfer from the hot coffee to the ambient. Okay, hot, cold, surrounding the ambient room temperature. Okay, you want to study the process of the heat transfer. Okay, so normally, okay, you in order for you to analyze the heat transfer process from the hot to the cold, you have to define first. Okay, in order to calculate the total energy transfer or the total heat transfer between the cup and the surrounding, you said that you mentioned that you are going to analyze, consider the process at during 5 minutes maybe or 10 minutes. Okay, for example, this is the 5 hours from 8 a.m. to 1 p.m. You put the coffee at the table from 8 a.m. to 1 p.m. Okay, but you want to calculate the energy or heat transfer. Okay, so you said that we consider the closed system in energy in equilibrium or energy balance at only during 10 minutes or 15 minutes. So that 10 minutes or 15 minutes is within maybe 8:30 to 8:45 a.m. Okay, so you only calculate and you only consider the equilibrium state during these 15 minutes. Okay, you only state that we consider the state is in equilibrium within this period of time. Bukanlah doesn't mean that the whole system doesn't move or doesn't change, but only at a small period amount of time we consider as if it is balance doesn't change, because we want to calculate to analyze the process, to calculate the energy or etc. Okay, so the thermal equilibrium that we consider, for example, is just within that 15 minutes. Okay, so that we can characterize the calculate the process. Okay, and then mechanical equilibrium is saying that no change in pressure at any point of the system with time. Phase equilibrium. Okay, if a system involves two phase and when the mass of each phase reach an equilibrium level and stay there. Okay, so this one where the process involves, for example, an ice. You have ice, I told ice cube, and you also leave the ice in the room temperature, so the ice will melt down. Okay, melting. So there is a phase change from solid, the ice cube, to liquid, the water. Okay. But when you want to study to measure the physical properties, the properties just now, energy, etc., you it's as if you consider at one time, at a certain period of time in the equilibrium, the means that the water, okay, the cube has reached, during that period of time there is no change of phase. Okay, only that particular period of time that you are going to study. Okay. And then chemical equilibrium, if the chemical composition of a system does not change with time, there is no chemical reactions occur. So the same thing, during that state of equilibrium, we consider that there is no change of chemical composition. Okay, but throughout the process can be throughout the whole process, for example 5 hours just now, throughout the whole process that can be change of chemical or change of phase, mechanical, etc. But during at one particular time that we want to analyze, we consider it is in a state of balance. Okay, I hope that you understand what I'm talking about. Okay.
Okay, doktor, faham.
Okay. State postulate, the number of properties required to fix the state of the system is given by the state postulate. Tak berapa, not really important. Okay, process and cycle. Ada berapa slide? Saya rasa ada lagi 3-4 3 to 4. Okay, process and cycle. Okay, process. Any change that a system undergoes from one equilibrium state to another. Okay, process. Okay, saya pun boleh tak. Okay, process. Okay, state, for example, from state 1 to state 2. Okay, ni simple, understand. So that is what we call a process. Path, the series of states through which a system pass during a process. To describe a process completely, one should specify the initial and final state. Okay, this is in mathematics, right? You do engineering maths. So process from state 1 to state 2, right? Process. Okay, but the path, okay, this is given the green line. Okay, this is, for example, this is the path one that you can take. So from state 1 to state 2, you can also have this path. Okay, so this is your second path. Or you can also have this path and arrive from state 1 to state 2. Okay, so that is path. Okay, quasi-static or quasi equilibrium process, when the process proceeds in such a manner that system remains infinitesimally close to an equilibrium state at all times. Okay, another definition. Okay, sometimes we doesn't specify the process to be equilibrium, but we say that it is quasi equilibrium, means that nearly close to equilibrium. So when a process is in quasi equilibrium, means that we still can apply all the laws the same as in the equilibrium state. Okay, so this one is used when okay, slow compression and very fast compression. Okay, if we have a slow compression, macam mana compression? Okay, slow compression process. Okay, then we define very non-quasi equilibrium lah. Okay. Okay, so when we have a slow compression process, we compress the piston very slowly. So we when we want to study the at a certain amount of time of the process, we state that the process is in quasi equilibrium, means that we just want to capture at a certain part, a certain period of time of the process. And while if we have very fast compression, non-quasi equilibrium, so it's like equilibrium, because the process is very very fast. Okay, so it's like we have to consider that as if the process is being stopped at one point. Okay, difficult to explain, but just to mention that if we classify a process as in quasi equilibrium, you can still apply the same law, the same principles, the same equation as in equilibrium or state balance process just now. So sama je, okay? Cumanya just that depending on the types of process, sometimes it is hard to classify a certain process as simply equilibrium, because the process is very very fast. For example, the high speed gas flow kan, very, very the movement of the fluid in the gas power cycles is very at high velocity. Okay, so we need to call we identify it as a non-quasi equilibrium process. But it's okay. Just want to say that you can apply the same principles. Okay. Process diagrams plotted by employing thermodynamic properties as coordinates are very useful in visualizing the process. Okay, the prefix ISO. Okay, this one. Okay, there are some name that we use to identify this process, which is the most the one that we usually use in thermodynamics is isothermal. Means that isothermal means that we assume that the process from 1 to 2 is temperature is constant. Okay, isothermal. If it's isobaric means that from initial state to final state 1 to 2, we consider the pressure is constant. Only from state 1 to 2, not the whole process. Okay, and then isochoric means that the volume are constant. Okay, a cycle process during which the initial and final states are identical. Okay, okay, cycle. So this one, this one from state 1 to state 2, this is what we call a process. But if we have complete like this, 1 to 2 and 2 to 1, to back to 1, so this whole thing is called cycle. Okay, because you go back to the same initial point. Okay. So that is what we are going to use for a thermodynamic cycle. Okay, the cycle is repeated. Okay, the engine, in order for the engine to run, the cycle is repeated. Not only one cycle. Okay, next. Okay, only dua is like, okay. The steady flow process. The term steady implies no change with time. The opposite of steady is unsteady. Okay. The opposite of steady is unsteady or transient. Okay. Okay. Steady flow, steady, okay, macam cakap, okay. Steady flow means that we at a certain period of time. The term steady ni means that the all the values, the temperature, actually is actually the same as energy balance just now, the equilibrium state just now. Means that at a certain period of time, we consider that the whole system, the whole control volume is in steady form. Means it doesn't change with time. So for this, if you have equation later on, if you have energy balance that has equation like in terms of the partial derivative, ini engineering maths ada belajar kan? Okay. In terms of times, okay, the partial derivative in terms of time, if the process is steady, so this partial derivative will be zero. Okay, means that there is no change with time. Okay, for example, if you have pressure here, pressure, the partial derivative of pressure in terms of time for that particular period, we consider is as a, it's not that the pressure is zero, the change of pressure in terms of time is zero. Okay, you need to understand, not the pressure is zero, but the change is zero. There is no change. Okay, when we say that the process is steady. So a large number of engineering devices operate for long periods of time under the same condition, and they are classified as steady flow device. Okay, steady flow process. Okay, so all these of this component we are going to use, apply, turbine, pumps, boilers, condenser, etc. We will consider it as a steady flow process. During steady means the flow in and out. Okay, there is no change of no change with time. Okay, okay, but actually this is not real. Okay, so the real actual phenomenon that occur in real life is actually the process will never or nearly never, okay, will never be static or steady like that. Okay, static steady static, tak bergerak kan, no change, no movement. Actually in real it won't be like that, but for engineers, for scientists, for researchers, in order we if you want to study, to analyze certain problem, we need to consider that way, that the process is steady, that the process is in balance, etc. But in real, it's actually it doesn't static like that. Okay, so that's why in a more advanced study, we need to consider the dynamic change. But at our level, we can use a steady static balance flow process to is already enough for us to analyze the problem to study. Okay. Maksudnya nak cakap macam, sorry, I explain also in Malay, just to make sure that some of you understand clearer. Maksudnya macam any perubahan benda tu, dia sebenarnya dia always ada, dia takkan the whole thing mass ke apa ke, dia takkan static, takkan saja, dia mesti ada change of fluid kat mana lubang atau macam tu kan. So dia akan effect sebenarnya the whole system tu. Tapi macam untuk kita for scientists, researchers, we need to sometimes macam kind of macam freeze kan process tu. Imagine that the process is freeze. We imagine, that's why ada imaginary boundary semua tadi tu. We have to imagine that the process is fixed so that we can fix dia sekejap, so kita boleh analyse dia, macam tu. Tapi sebenarnya real dia ada je perubahan benda-benda yang belakangan tu. That's why the dynamic measurement, dynamic value have to be included. So kalau macam for example, if you at your degree level, if your process or your system you consider is a steady system, um, uh, your experiment is in a steady flow process, the examiners can or okay, they can consider your results. Okay, but if you are doing postgraduate, you are doing master or PhD, when you say that we consider that this process is in steady form, then the examiner might attack you, doesn't mean that you are wrong, it's just that they will trigger you. Are you sure that there is no change in this part, etc., etc.? So how do you consider that, right? So if you are doing in the future, you're studying or you're doing research, more detailed postgraduate research, as example, you cannot neglige, you cannot lupakan you cannot neglige this dynamic change. Jadi tapi untuk this level, bachelor level, steady flow is enough. Okay. Under steady flow condition, the mass energy content of control volume remain constant. Okay. So it's just Bismillah. Okay. So last one, okay, we don't have that. I mean, I think we're already full exhausted juga nak buat ni, tak apa. So you can take a look. Later on, I will upload, insyaAllah, the slides and the introduction slide in Putra Blast. You can take a look first at the example exercise, and we will see if we have time to check next week. Oh, no, I'm not sure yet. Okay, because there's a lot to cover, to be covered. Okay, so I think that's all from me today. Chapter 1, basic concept of thermodynamics. Okay, do you have any questions? Anything to ask? Any comments? Semua okay? Stop ni.
I think all good, Doctor.
Okay, stop slide. Tadi. Okay. Okay, so just because I don't have the attendance yet, tapi I saya capture ni dulu kehadiran attendance. Okay, if no questions, then I think that's all. Okay, so I'll see you guys again next week, insyaAllah, Thursday, 9 a.m. Okay. Okay, everyone.
Okay, thank you, Doctor.
Okay, Doktor.
Question.
Okay, thank you. Assalamualaikum.
Waalaikumsalam. Thank you, Doktor.
Thank you, Doctor.
Thank you, Doktor.
Okay.